Hello and welcome again to my Physics Online video lecture series. Today's video I'm going to be talking about resistors in series and parallel combinations. This is the second part of this discussion. The first part I focused a bit on figuring out what the equations were going to be using just geometric considerations. How are we changing the length of the effective or equivalent resistor? How are we changing the area of the equivalent resistor for each of these combinations? Today I want to actually continue with a more standard approach to all of this. So the more standard approach, before I get into it, how does the standard approach really work? Well, basically we have to make use of conservation of charge and conservation of energy. In some sense, we're making use of what are called Kirchhoff's junction rule and Kirchhoff's loop rule. We're using Kirchhoff's laws. At this point in the course, we haven't really introduced those, so there's no special reason for you to know what they are. You just kind of have to take on faith that they work at this junction. Now, obviously in the future we'll talk about Kirchhoff's rules and you can go verify that they do work, so you're not literally taking them on faith. But if you are approaching this as a first time to do physics kind of course, you wouldn't be familiar with these laws yet, and if you're following along in a textbook, they would not have been introduced yet in most textbooks. And yet, most textbooks also use the approach that I'm going to use today to derive the equations for series and parallel. So they kind of end up having a little bit of a logjam here, in as much as you end up having to kind of assume as true something that is true but that is not yet established as true in order to prove something else. So that is kind of why I like to spend time on the other method, because there's a little bit of like assumption in as much as we just say, like, what if these are equal resistors that you're combining this way or that way to make the math a little easier on ourselves. But it's not really an assumption. You're just making use of what we already know about the how resistance works, resistivity, length, area, geometric parameters. So what do we end up doing for this sort of standard approach? Well, we can consider them in either series or parallel. So considered in series, we end up having a simple diagram like this. We just basically just put them end to end to end to end, and to solve, we kind of say, well, what if we actually connected this combination up to a battery or some other sort of power supply so that we're going to have current allowed to flow through the system. So we'll draw the current maybe in green just for contrast. So the current basically is going to end up coming around the system like this. And essentially, we claim that the same current is present in each one of the three resistors. This is another way of saying that charges aren't being used up. So charges must complete this circuit. They can't just appear or disappear as needed. A charge that exists here and is being pushed around the circuit basically has to go through this element, then it has to go through this element, then it has to go through this element. Now let's call the battery down here just a voltage source. We'll say that it has V total. Now V total is basically like how much total work can be done on this charge as it moves around the circuit. And some amount of work is done in pushing it sort of like through this resistor. Some more work is done getting it to move through this resistor, and some more work is done moving it through this resistor. That's another way of saying that I expect there to be a voltage drop here, another voltage drop here, and a third voltage drop for this resistor. And as I have other resistors, there might be additional. Well, the total must be equal to the sum of the individual amounts of work done, and therefore the total voltage drop is the sum of the voltage drops across each of my resistors. And I'm going to put a little ellipsis here because we could have 4 or 40 or whatever. We might even only have 2, in which case delta V3 and all other terms after it are 0. But I'm going to do 3 for now. Okay? Ohm's law says that delta V1 must be I times R1, and delta V2 is I times R2, and delta V3 is I times R3. That means that my delta V total is equal to I times R1 plus I times R2 plus I times R3, etc. And that in turn means that I can pull an I outside of everything. And so I just have I times a series of R's added together, like so. Now, the idea behind this equivalent circuit analysis is that we should be able to take this existing circuit and take all the resistors out and then hook up to a new equivalent resistor, and that equivalent resistor will have the same current pole as this series did from the same battery or power supply. And so basically we end up with a simplified circuit that looks like this. But by Ohm's law, this one just says delta V total is I times R equivalent. So if I notice that I have a delta V total here and I have a delta V total here, I can set the two sides equal to each other. And so what that means is that I times R equivalent is I times R1 plus R2 plus R3, etc. And so if I divide an I out of both sides, then I just end up with R equivalent is R1 plus R2 plus R3, etc. Or if you prefer summation, you'd have the sum of the RJs. So that's the series circuit. Now let's turn to the parallel circuit. The parallel circuit basically looks like this. I've drawn for 3 resistors, but I've also allowed for the possibility of more. Note that this is a complete circuit without adding anything more up here, that I can have current flow out of the battery, move through resistor 1 and come back. I can have it come out, move through resistor 2, come back, etc. And so in some sense what I have is a total current that is leaving or returning to the battery, which I'm going to draw here, and I'll label this as I total. And then through each individual resistor, I have some current. We could call it I1. I have a current I2 here, and I have a current I3 through here. Okay. And again, I have Ohm's law, so I can make use of Ohm's law for any given, and the Ohm's law for any given would say something like delta V1 is I1 times R1, and delta V2 must be I2 times R2, and delta V3 is I3 R3, etc. Now, how do we know that the current is different for each one of these? Well, it's allowed to be. And so since it's allowed to be, we have to kind of denote it this way until proven otherwise. Why is it allowed to be? Well, because an electron that gets to this point right here, for example, can either go this way or go this way. Excuse me, an electron hole. An electron is kind of going the opposite direction. And again, if I get to here, I can either have my charge go this way or go this way. And then these charges all end up kind of rejoining at the junctions and ending up back down here. So they flow like a current, but I could have, in principle, 20 charges come out of this end, and 5 go here, 15 go here, and up here I now have 15. Maybe 6 go this way, the other 9 go this way, and then with only one more option, all 9 basically come here. So now 9 joined with 6 gives me 15, joins with 5 gives me 20, and then that returns. So I had 20 out, 20 in. Basically what this means is that I can, on the one hand, write that I total is equal to I1 plus I2 plus I3. And if there are other terms, then I can add all of them as well. Now, these equations in turn can be solved to say that I1 is delta V1 over R1, and I2 is delta V2 over R2, and I3 is delta V3 over R3, etc. Okay, so that means that my total current, I total, is equal to delta V1 over R1 plus delta V2 over R2 plus delta V3 over R3, and any additional terms I may have. Now, where the sort of equivalent circuits thing comes in is as follows. By Kirchhoff's loop rule, delta V1 and delta V2 and delta V3 and any other delta V's will equal delta V from the battery. That's not super well explained in this video, and I'm not going to really explain it further here because of time constraints. But essentially, this is conservation of energy in action. The battery gives us the same voltage drop across each element in parallel. So if that's the case, then this I total I'm going to replace with a delta V over R equivalent, and that just becomes delta V over R1 plus delta V over R2 plus delta V over R3, etc. So now if I want to get the R equivalent, I can divide out a delta V from all terms. And so this right here leads me to 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3, etc. Or if you prefer, 1 over R equivalent is the sum of the individual 1 over R's. Since in the previous video I already did the simple combinations with like three in a series, 3 in parallel, 3 in series but drawn weird, In this video, for the example, I'll just do a set of 4 resistors that are in a kind of pair of combinations, if you will. It's more complex than just they're all in series, they're all in parallel. And so what we want to do is look at how to analyze something a little more complex as our video example. Essentially what we have here is that these two are in parallel with each other, and then these two are in parallel with each other, and each parallel pair is in series with the other parallel pair. And so basically what we would do here is we would combine these two into an equivalent resistor that we might call like R12, and then we would combine these two into a resistor that we will also call R34. So this will be R34. And then this entire combination is just now a simple pair in series, one of them being R12 and the other one being R34. And so we expect the total combination's equivalent resistance to be the combination R12 plus R34. So now what we want to do is basically go back and solve for each of these two in turn. So this set in parallel, what we would end up with is 1 over R12 is 1 over R1 plus 1 over R2. You can plug in the numbers, so we have 1/12 plus 1/24. Whoops. And recall that 24 is 2 times 12. And so I have 2/24 plus 1/24, which is 3/24 ohms. And that means that 1 over our equivalent is 3/24. And so R12 would be 24/3 or 8 ohms. I can do the same thing over here. 1 over R34 is 1 over R3 plus 1 over R4. So that's 1 over 18 ohms plus 1 over 36 ohms. Now the combination of those two gives me 1 over R34 is equal to 3/36 ohms. And so that means that R34 is equal to 36/3 or 12 ohms. And so that means that the equivalent for the whole system, and maybe I could do this one out in green just for contrast. So our equivalent is therefore 8 ohms plus 12 ohms. And that means that our total circuit equivalent resistance is 20 ohms. So, and that is your parallel combination for resistors. Now note that in doing these two derivations for series and for parallel, I ended up getting the same results that I had with the geometric arguments here. So that's all I'm going to do in today's video. Thanks for watching.